We will now be moving on to our next speaker. Our next speaker is Dr. Ravi Vadapalli. He is the Director of Advanced Computing at the Institute of Data Science and Computing, University of Miami. And he's also a Research Associate Professor, Electrical Computer Engineering at the College of Engineering of University of Miami. He has more than 20 years of experience in harnessing high-performance computing and data science and analytics across diverse domains. We could not have Dr. Vadapalli live with us today, so he has sent a pre-recorded video of himself, and he will be talking about on how data science can be used for advancing economic innovation through industry and research partnerships.
Thank you, Dr. Yakonik, for providing this opportunity to participate in this conference and share my thinking on the role of data science and engineering in higher education for economic innovation. Since it is a recorded presentation, if you have any questions or interest in collaborating on some of the areas that I'm going to discuss today, please reach out to me by email at rxv441@miami.edu or by phone in the listed here. I'm the Director of Advanced Computing Systems at the Institute for Data Science and Computing and Research Associate Professor for Electrical and Computer Engineering. The Institute is poised to converge data science and high-performance computing for research innovation and industry research partnerships. Therefore, this particular presentation and our work is very relevant to our institute's vision. Let's first talk about the dilemma. What is cyber infrastructure? Cyber infrastructure is computing, storage, visualization, assets for information exchange and computing. Cloud computing emerged as pretty much has revolutionized the cyber infrastructure access across various stakeholders. In the past, higher education systems had deployed cyber infrastructure capabilities for research and training. With the emergence of big data, the utilization of computing emerged to be a prominent feature in all worlds of data consumers. That includes higher education and industry. Fundamentally, the attractive cost structures and most importantly, elimination of capital expenditure for operational expenditure or even product expenditure or productization expenditure evolved to be cloud computing's best feature. Furthermore, the ubiquitous access to tailored application-specific heterogeneous computing resources has shown that cloud computing is here to stay. Great. So what is the problem? Before we get into the problem, let me also cover the other side of the story. How cyber infrastructure is utilized in higher education and industry. In higher education, there are a variety of domain areas: public health, psychology, computer science, engineering, material science, manufacturing, climate science, law, legal analytics, variety of them. Each domain area has a specific interest and requirement of computing resources. Because of various resource availabilities or needs, there is always access to technical support that complements the hardware deployment for ease of access and optimal utilization of computing services across various domain areas. In cloud computing, that is missing. There is no technical support. So broader CI adoption or cyber infrastructure adoption across research innovation using cloud computing is not easy, especially for some users who do not have abundant support for buying technical support. Okay. In the industry, cloud utilization in industry is pretty straightforward. They just come, use the off-the-shelf tools for business viability, growth, investment, sustainability, the business-like functionalities. Therefore, there is not enough innovation requirement in industry's use of computing, whereas there is a tremendous requirement and interest in higher education for innovation in cyber infrastructure utilization, writing new algorithms, designing new softwares, testing new paradigms, developing new technologies. That's all under the higher education. Companies will come and use and go. Because of this difference in utilization of same computing resources, there are two fundamental issues we need to address. The issue number one is identify the technical capability or technology mindset that will glue the computational tools with domain research needs. That's number one. Number two, these expertise has to connect with industry in developing the next generation tools. Okay, because of these requirements, the missing link between cyber infrastructure in higher education and cyber infrastructure in industry, which in other form called cloud computing, is the human technology gap or the technological expertise that can forge the partnerships. With that, we redefine the data science to be higher education data science and industry data science. They are not same. Higher education data science is a variety of domain areas, diverse data sets, variety of algorithms and tools. Industry data science is largely data-driven with a focused interest in certain functionalities relevant to the business. Innovation is minimum, utilization is maximum in industry. In higher education, innovation is maximum, utilization is also equally competitive in higher education. So with that mindset, I propose that we need to develop convergent skilled workforce that is transformative across these two paradigms, the industry and research. Why are we talking about this now? As you can imagine, many universities and institutes are growing in their enrollments of data science students, and they're creating new data science and engineering programs. Wealth of opportunities from industry demanded this creation. So higher education is creating programs to feed the students into industry. Students are coming to higher education to go back to industry. But the important aspect is, are these students really going after the industry for the stated purpose, or do they need to be exposed to different tools and technologies to be able to be more productive in industry? With that thinking, we redefine the data science. This is a brain model. The left brain is market science. The right brain is domain science. In market science, you use off-the-shelf tools and technologies readily accessible to evaluate business productivity or goal. So in this case, you use Python, Spark, Hadoop, or other machine learning, deep learning, or statistical analysis. Heterogeneous computing. Why heterogeneous computing? Because the business processes are statistical events, and therefore we are not writing a more model-driven analytics on these business processes. I'll tell you what I mean by that when I talk about domain science. In domain science, we use homogeneous computing largely because the complex modeling and simulation of physical phenomena in domain science involves large amount of communication between processes in a parallel computing environments. In distributed computing environments, the communication is not as much as computing, and therefore heterogeneous computing resources are okay. If communication intensive processes get involved, if you have heterogeneous resources, so you need to worry about more communication overhead or other overheads due to heterogeneity of architectures. I don't want to make your life more complex here by thinking about all those things. But in general, in a brain model, you have a left brain of market science of profitability thinking. On the right side of a right brain, you have a model of addressing a better understanding complex phenomena. The algorithms and tools you develop for understanding complex phenomena can be applied in market, and optimization tools used in a market can be applied in physical phenomena modeling and simulation as well. For example, take climate science. In climate modeling, different small-scale models of air, water interaction, ocean interaction, or aerosol interaction, these are small-scale models, can be integrated into a very bigger model about how tornadoes occur, how hurricanes occur, how do we prepare for hurricanes. It's a bigger model. So several small models or machine learning models, a combined model could be a large-scale model that involves some physical phenomena of climate science. Similarly, in complex physical phenomena can be divided into multiple small models to better understand the intricacies of physical phenomena. Okay, enough of that. Okay, so data science is now redefined to be market science and domain science. If you look at the computational research paradigms, there are two paradigms: high-performance computing and big data. High-performance computing is, like, if we go back here, all the right brain strategy is with high-performance computing, and all the left brain strategy is with big data, right? So with that context, high-performance computing involves modeling and simulation of complex physical phenomena. Big data, data science will be applied in HPC to better understand the interdependencies of various parameters in a simulation environment. But in large, these models are communication intensive. Therefore, we use high performance computing. In big data, the communication overhead is far less or minimal compared to computing. Therefore, in big data, the statistical methods and optimization strategies are heavily used. There are applications in between, interchanging between big data and HPC and vice versa. That is the reason we define a data science and engineering component where we converge HPC and big data for science engineering innovation and economic opportunities. This data science and engineering component involves current technologies as well as emerging technologies such as neuromorphic computing, which is brain model utilized computing. Quantum computing depends on quantum mechanics or exponential computing. and graphic core processing, etc. Okay. So we talked about the cyber infrastructure and in how it is utilized in higher education and how it is utilized in industry. We found technology gap. Our workforce that is needed to address the gap between technologies and human needs. Then we talked about dividing the data science into market science and domain science. And now we are talking about how this exploration helped better understand the student training strategies for the convergent training. So first experiment is we took about 300 students across 2 semesters for a course that is a graduate course taught in University of North Texas. And the course number is CSCE, Computer Science and Computer Engineering. 5300, 5300. You can read this online. The course is an introduction to data science and big data. So we talk about data science fundamentals, big data fundamentals, and then introduce them to some machine learning tools. In the course, we asked the students write a concept paper which covers 4 elements. They have to provide a hypothesis of anything that they are working on or they think they can apply data science on. And they also have to provide the business case, why this hypothesis is needed, what it displaces or where it helps. And then they have to provide a third element, which is technologies and tools that they're going to use in an implementation. They don't have to implement, but they have to mention what tools and technologies they're going to apply. They cannot simply say, I'm going to use Python. They have to give a little detail about why they use what they use. And they also have to give an impact. Should this technology becomes a viability, how does it impact the existing markets? Okay, so the main purpose is to identify how connected the students are with the data science and to bring about their engineering and entrepreneurial skills. Top 5 papers for each semester will be matched with the faculty. The first semester students, 5 of them, 2 PhDs and 3 masters. All students originally enrolled in the course to graduate and find a job. That is what they mentioned in the pre-course survey. At the end of the course, 2 students converted their master's program into doctoral programs, and 3 students chose to do research in lieu of complete coursework. All these 5 students were matched with the faculty, and some students even have been helping projects that are currently funded through federal agencies. Okay. Additionally, by working with these students, the faculty also got traction into these projects and they established their research areas and also found funding. Okay. Overall, it became a win-win scenario for all stakeholders. Then in the first experiment, the students are drawn from computer science and engineering. So they are from computer science, computer engineering, data science, artificial intelligence, information science, cybersecurity, data engineering, and social sciences, this type. They're coming from all types of courses, taking the data science course. In the second experiment, we focused on one set of students, all doctoral students in bioinformatics. At the University of Miami, this course is offered, advanced graduate level course for doctoral students from Miller School of Medicine, Biomedical Studies. Okay, there are 12 students, all are doctoral students. The important part is all of them are wet lab or experimental students that do not know anything about computing. we taught the course to them and then made them write concept papers on how they will utilize the data science tools we are discussing in their ongoing research activities. Okay, so that is the second, and the details are provided in the link and the QR code. You can read the complete story about it. Okay. The third experiment is in progress. This is not done yet. It is in progress. This experiment is convergent data science. See, in the first time, diverse domain areas are integrated into data science program. Second experiment is a specific curriculum provided for a specific domain. Now we are expanding it into multiple domains through collaborative teaching and experiential learning. In this model, we provide data science curriculum to all students and then divide them into batches of that are interested in climate science and that are interested in additive manufacturing, 2 domain areas. And then what we do at the end of the curriculum is to expose students to other data sets. That means a climate science student will be given additive manufacturing data set and vice versa. By doing so, we will expose students to foreign data sets because data sets do not come as cleanly as we see in the academic programs. Academic programs will provide small data sets, very clean versions, no issues, so that we can provide initial experience to students. In these particular expeditions, we want students to be exposed to data gaps, how they analyze missing information, how they analyze the missing data, and how they analyze their models on different data sets. So for example, in the graphic here, you see that it's an additive manufacturing process where you start with a powder and prepare a part. This is different from conventional manufacturing where you make a part and shape or cut it to refine to be a useful part. In cutting for a part, there is a lot of material wastage. In additive manufacturing, you're fusing the material to make the part, so there is no wastage. But it is expensive, and there are so many issues right now in additive manufacturing where the part look exactly the real part, but the mechanical, thermal, or other electrical properties are not the same. Still, there is a lot of work need to be done. Okay, so the benefit that students get is to better understand different data sets, data gaps, and also understanding how different models can be applied. So more like an out-of-the-box training and bring about their entrepreneurial thinking. So not all students will go find jobs. Some students may use these technologies and tools and training to open their own business. They may have different ideas about market or other physical aspects. Okay, so we wanted to provide that environment to them. Okay, so key takeaways are data science is redefined. We divide it into market science and domain science, and we impart students with additional knowledge of both. In addition to computing, they have to be equipped with understanding and processing data and also write software to model the data on computing environments. So they will be equipped with software, data, and computing. The second aspect is the students that are trained in diverse domain science areas in higher education during their graduate program will develop transferable skills from higher education into industry. They will provide additional connectivity between industry and academics for increased partnerships in research innovation, economic improvisation, or economic opportunities. And the third aspect is that this transformative workforce will also help create new programs and new economic opportunities through working in industry as well as creating their own businesses. Okay. And thank you for the opportunity once again. And if you are interested in this model and like to participate in this study or like to collaborate in any parts of this work, please reach out to me. You can write me an email or connect me on the LinkedIn. I would love to talk to you and see where we can collaborate. Thank you. I once again thank the organizing committee for this conference and for the opportunity to share my thoughts.
We would like to thank Dr. Vadapalli for such a detailed presentation in how data science can be used for advancing economic innovation.